So it's the first seminar of the GDO program. So today we have Dror Bar-Natan. He's going to talk about meta groups, Meta-Bicrossed-Products, and the Alexander polynomial.
Hello. So first of all, my talk will follow a handout, and I hope all of you have a copy. There should be copies in the back if you don't, and here's the handout in full. Second, here's the worst. So, you know, there will be a bit of ugly formulas, and this is the bit of ugly formulas. Oh, I forgot my point. Good, you have a pointer. Even better than mine. So, here's the bit of ugly formulas, and you know, in my defense, I will say that they're not much more than row and column operations and the like on matrices. And you know, if you compare it to like the complexity of adding velocities in special relativity, well, it's, you know, that's about how complex this is, right? Okay. Now for the actual content. So, what do I want to say? So, you know, I'm here because, well, actually because I wanted to do something else, but something that came out of it is a pretty good way of computing the Alexander polynomial, and I'll explain what I mean in a few minutes. But some people here might be here for a different reason, which is I'm going to define a meta group and give a few examples and a meta-Bicrossed product and in general meta structures. And apart from being lovely and useful, and I really mean useful because, you know, I really can do things that you can't do without them, or for which the language will be more complicated without those structures. So apart from that, I mean, you may want to tell me that I'm being silly, and really these things were studied a long time ago and should be named something else. And I never gave this talk in front of an operatic audience. So I mean, people who know all about algebraic structures will tell me mine is actually well known. So I usually give it in 1 hour, so now I have 2 hours, so you see I'm intentionally slowing down, actually, right now. And I should say that the work is closely related to work by various people named here, and you're welcome to look up their work and make the comparison. So maybe first of all I will tell you where things came from, because I'm actually not going to talk about these things, but I just want to say that they came from somewhere else. So really they were coming from talking about two-dimensional knots in R4, and I wanted to tell you a few things about two-dimensional knots in R4, and even though really I'll hide this for the rest of the talk. For the rest of the talk, two-dimensional knots in R4 will not play a role. I will sort of project it down to 3 dimensions and talk about 3 dimensions. But, okay, so what about two-dimensional knots in R4? So here are 2 ways, here are 2 perspectives, okay? So one perspective is, you know, summarized by this video clip. So right, R4 is movies in R3, and if you have a 2-dimensional thing in R4, and then at any time slice, you see a 1-dimensional thing, and generically it will be a ring, okay, an S1. So if you look at a knot in R4, it will look like a movie of rings in R3. And in fact, more precisely, a movie of rings in R3 is like the 2-dimensional analog of a braid in R4. So it's a 2 braid in R4, okay? So what can flying rings do? So flying rings can do the same as moving points, namely they can trade places, right? But this is boring, actually, or more boring than the corresponding thing in R2, or meaning in R2 cross time. Because in R2 cross time, there is this interchange and there is this interchange, and they are distinct. Whereas in R3 cross time, you can interpolate between them by going like that. So in fact, these crossings are sort of, not quite trivial, but they behave like permutations in R4. However, there are two other types of crossings. Green can fly through orange, and therefore they can trade places, or orange can fly through green, and they can trade places. Okay? And in fact, it turns out that the fly-through part of braid theory, of W braid theory, as it's called, so let's define braiding in R4 of two-dimensional things to be W braids. So it turns out that the fly-through part of W braids is exactly equivalent to the ordinary braid group. However, you have an additional thing, which is the external sort of transposition. So W braids are strictly richer than ordinary braids. They are strictly more. It's a bigger group. Okay? And likewise, so the thing can be generalized to knots, and so to knotted two-dimensional things, and knotted two-dimensional things are strictly more than knotted one-dimensional things in R3. Okay? On the other hand, as it turns out, their sort of quantum theories are somehow less, but it's not entirely nothing. It's manageable. It contains the Alexander polynomial. It contains more than the Alexander polynomial, but we don't know how much more. But it's still weaker than the corresponding theory in R3. So that's one point. The other point is that there are lovely operations on two-dimensional knots in R4. So in fact, in R4, you can talk about knotting of two-dimensional things, but also of one-dimensional things. So schematically, a knot in R4 will be a knotting of a number of spheres, balloons, and a number of hoops, so one-dimensional things. Okay? And now, suppose you have a knotted K, like that. So suppose you have a knotting of a number of balloons and a number of hoops, and I'm assuming that everything is connected to a base point, okay, via one-dimensional strings, okay? Then there are a few operations. So there is an operation which I will call head multiply, okay, so HM, and this operation is like the product in pi 1. So if you have two hoops or two paths, you can compose them by going along one and then along the other. So this is the composition of the X part of the knot with the Y part of the knot to give the Z part of the output knot. Okay? And notice that it's a unary operation. It's not like, it's like multiplication in pi 1, but it's not multiplication in pi 1. Okay? The input is a single thing with two components, and the output is a single thing with one component. It's not that the input is two independent things. If the input was two independent things, they wouldn't be knotted with each other. They wouldn't be tangled with each other. Here, the X and the Y could be tangled with each other and with the other parts of the knot. So it's a different story. Okay? Okay, likewise, there is an operation which I will denote by tail multiply. And tail multiply is like the parallel of or the analog of multiplication in pi 2. So you take two balloons and you join them together and you get a bigger balloon, okay? And again, yes?
Your symbol like that, it's just a symbol of the
Oh, yeah. I should have said it right at the start. You know, the little circle operation should be banned because it goes the wrong way, right? When you write x goes to y goes to z, the little circle operation, you know, so you have f and then g, and the little circle operation will be g circle f. So double slash is defined to be circle op. Okay, so it's composition done right, and it's also applying a function. So this means, so the notation here means apply this operation to this element, and if I wanted to apply a further operation, I'll do another double slash and put it on the right.
But that was not my question. My question is...
Oh. Well, okay, but still I got the chance to make a political statement, and, you know, that's worth it. I'll make more, you know. Are there British people here? Okay, never mind, yeah?
This symbol which is
Swiss people.
You know what, sorry, are there Canadian people here? So I can say things about the Canadian Queen. Okay, sorry, what were you saying? What? I know I'm on video, it's okay with me. Sorry, what were you saying?
Because you talked about these knots in R4, is this a symbol for that? Or, I mean, there was a quantum jump between the previous discussion.
Yeah, this is a knot in R4.
It's a symbol which represents what you were talking before.
Yes, except now it's a knot that has several components, some of which look like balloons and some of which look like hoops, okay? And what I'm emphasizing is that there are operations. It's an algebraic structure, okay? Now also...
So should we understand what that picture means, the two balloons and the two...
Well, it's a symbolic for a knot in R4. I mean, it's drawn as the trivial knot, but it's not the trivial knot, right? It's the... it's not necessarily a trivial knot. So this is a symbolic for a knot in R4, which has two components that look like spheres and two components that look like S1s, and they might be embedded in some complicated way in R4.
And the lines
and
middle mean...
Well, and then the spheres have a base point, and they are and it is connected to some global base point, and so do the hoops. Okay, so it's all sort of connected by strings to some middle point, and these are the things that I want to, or that I temporarily want to study, the knottings of that. Now, on knottings of this, there are operations. Wait a second, my computer is not getting power. That's not good. Well, okay, it will survive for the hour, but I should remember to occasionally move something so that it will not sleep. Anyway, so there are operations on such knots, and I'm just telling you what they are. There is the head multiply operation, there is the tail multiply operation, and then so this is like multiplication in pi 1, this is like multiplication in pi 2, yes?
And in this picture, that bullet, in principle, it can be something inside it, so, or...
The bullet?
Yes.
No, the bullet is a point. It's just a base point.
So they are really interconnected, like, so other potential components of the knot, where in this picture can they be? So you're saying that this...
So it's a single component, or not a single component. The knot has several components, some of which are S2 and some of which are S1. Except my convention is that all of them are linked to a base point by a path, to a single base point. So the things I'm studying right now for the next, 2 minutes are, well, take this topological space and look at the set of its embeddings up to isotopy in R4. Okay? Okay. And I'm not telling you that things should be oriented, there should be directions, or there's a little bit of extra complexity, okay? But it's not interesting. Also, Okay, so again, now I have two operations. One that isn't multiplication in pi 1 but looks like it. One that isn't multiplication in pi 2 but looks like it. But then there is also a third operation which isn't the action of pi 1 on pi 2 but looks like it. Okay? So basically, the operation, well, I'll call it the swap operation of u and x, where u is a balloon and x is a hoop. And the operation will be to take the string of the balloon and pull it around the hoop x. Okay? And again, it's a unary operation. Its input is a single knot, but it looks like the operation of pi 1 on pi 2, the action of pi 1 on pi 2. So I'm still telling you where I came from. And so take this algebraic structure. You can talk about, you can look at formal linear combinations. You can talk about the augmentation ideal. You can form an augmentation ideal. Oh, sorry, you're right. I need one binary operation as well. So the binary operation will be, so if you have two such things, you can put them side by side and then merge their base points. Okay? So, but anyway, you can talk about augmentation ideals. You can talk about degraded completion. You can talk about finite type invariants or a maps Z, like I was talking about last week. And you'll get a fancy invariant of such things. So this invariant is not what I will talk about. Now take this fancy invariant, and it will be valued in some space of, well, related to Freely algebras somehow. Okay? Freely algebras and cyclic words. So take that fancy invariant and mod out by a relation that kills practically everything, but not quite everything. That kills a lot of the stuff. So make it somehow almost commutative, but not quite commutative, by killing almost everything. And you'll get a weaker invariant. Now, it's still a perturbative invariant. It's still an invariant, a graded invariant, defined degree by degree. But you look at that simpler invariant, and you find that basically the series that appear in it can be summed. So you'll have things that look like e to the lowercase t happening inside the formulas for that invariant. You'll have lots of things that look like e to the lowercase t. And then take these things, and wherever you see an e to the lowercase t, replace it by a capital T, an uppercase T. After you do that, so basically after you sum the perturbative invariant, which is a quotient of the universal perturbative invariant of this thing, you will get the thing that I will talk about. So now I should, proceed and start and continue talking about the thing that I really should be talking about. Okay? But before that, a few words about knots. Okay? So here is a picture of a knot. Ignore for the moment the red and the green, so the numbering. Okay? So a knot for me is a picture, a graph in the plane, or a quadrivalent graph in the plane, where the vertices, so here is a vertex, have some further information, which is sort of which strand is over and which strand is under. So this is actually a knot diagram. A knot is an equivalence class of such pictures modulo some famous relations, the so-called Reidemeister relations. So the Reidemeister 2 relation says that, well, you can slide, the upper strand to the left, and then you get this picture. The Reidemeister 3 relation says that, well, if you have a crossing and then a further strand sort of under the whole picture, then you can slide that further strand up, and it will become like that. And the two things are topologically equivalent, and so the Reidemeister theorem says that two knots are equivalent if and only if you can get from one to the other by a sequence of such move, including the further move Reidemeister 1, written here, which I have written in gray. I grayed it out because it's sort of special, it's less interesting. So the reason it's less interesting is because if you don't mod out by Reidemeister 1, the theory hardly changes. Because what happens is basically R1 allows you to undo kinks. If you don't mod out by R1, you can get you'll have extra kinks in the knot, which you will not be simplifying. But those kinks commute with everything else. So, you know, if you have a kink here, you can slide it wherever you want using the other moves. So basically, if you don't mod out by this relation, the only extra information that you get is somehow a counting of the kinks. Okay? So basically, you get a z worth of further information, and knot theory is much bigger than z, so adding or subtracting a z factor is not a big deal. So therefore, I will not mod out by Reidemeister 1. Okay? So that's what a knot is. Now, actually, I care about something else. I care about tangles. And a tangle is like a knot. So it's a picture made out of crossings. Okay? But it's a picture drawn inside a disk in the plane. Okay? And again, it's the same kind of picture, and you mod out by the same R2 and R3 relations. Do not mod out by R1. And the reason I care about tangles is because if you understand tangles, then you understand knots a little bit better. So for example, if you cut a knot in the middle, so suppose you cut the knot here, the part below the cut is a tangle. And the part above the cut is also a tangle. Okay? So suppose you had a complicated invariant of a knot to compute. If you could extend this invariant to tangles, then you could compute the first half first and then the second half later, and then use whatever formulas are available to compose the two halves. So the point is to have, you know, invariants for which there are good composition properties. And that's somehow the divide and conquer method for computing invariants. And in fact, in some cases, it leads to a significant reduction in complexity. So essentially, if you have an invariant which is computable in exponential time in the number of crossings, then you know, half a knot will have n over 2 crossings, and the time it will take to compute it will be e to the n over 2, and twice e to the n over 2 is a lot less than e to the n. So by dividing, you can actually save a great deal. Of course, then you'll have to pay the price of gluing. So if the price of gluing back again is not too much, you've actually saved a great deal. Okay, so that's why I care about tangles. Also, various theorems about knots become simpler or easier to prove if you're allowed to somehow concentrate on the part of the knot that you really want to study. So that's why I want to extend my invariants to invariants of tangles. Okay. Now, so I'm still in preliminaries. I still haven't started my talk. So the next preliminary is the classical Alexander polynomial, and I want to tell you a few words about it. So the classical Alexander polynomial is defined as follows. Well, first of all, you label the arcs of the knot 1 through n plus 1, where n plus 1 is again equal to 1. So an arc is an uninterrupted piece of string. So kind of I consider, well, okay, so this whole thing is an arc, and it's not because the other thing goes below it, it doesn't interrupt it. Okay? So also, I guess 4 goes from here all the way to here. Okay? So if you have an n crossing knot, you'll have n interruptions, and therefore n plus 1, well, I'm taking long knots. So n plus 1 arcs, but I'm identifying the last one with the first. So I label them 1 to the number of crossings, so 1 to 8 in this case, in green. Okay? Now you look at the vicinity of each crossing. I suppose I should have told you that crossings have a sign. And there is a certain right-hand rule for determining the sign. I don't think I want to tell you what it is. Okay? But anyway, if you have a positive crossing, there will be 3 arcs surrounding it. And likewise, if you have a negative crossing. So what you will do is you will form an n by n matrix whose rows and columns correspond to the arcs. And then if you have a crossing like that, then in row C, so in the row corresponding to the outgoing lower strand, you will add 3 terms, 1 in column A, 1 in column B, 1 in column C, and these are the terms. Okay? Likewise, you will do for negative crossings, and doing this for all crossings, you'll get an 8 by 8 matrix. Okay? Here is the matrix that you get. You can check it. Okay?
Assume on 0 element in each row and each column.
Yes. Well, generically, yes. Okay? I mean, there are special cases where, A could be equal to C, or B could be equal to A, and then things will change a little bit, but generically, you're right. Anyway, take this n by n matrix, compute its determinant, it turns out to be 0 for a trivial reason. However, if you remove its last row and last column, and then compute the determinant, so in computer code, you take this matrix, you take row 1 to 7 and column 1 to 7, and you feed it into the determinant function. You hit enter, and you get an output, and that output is a polynomial, and this is the so-called Alexander polynomial. It's determined up to a unit in the ring of Laurent polynomials in X. So I mean, here we got a polynomial, but if you but for different presentations of the same knot, we could have gotten the same polynomial multiplied by plus or minus x to some power. Okay? So that's the Alexander polynomial. Now, suppose I wanted to do, even before that, the Alexander polynomial is actually very easy to compute. It's a matter of computing a determinant. And computing determinants, well, you know, if you're being silly, it takes you n factorial time. But if you use row and column operations, it takes n cubed time. So it's really a fast computation. Okay? However, the computation departs from topology. Because when you do row and column operations, you get all sorts of intermediate matrices that mean nothing, that don't have an topological interpretation. I suppose, I didn't tell you where this matrix came from, but it came from measuring something in topology. So this one does have a topological interpretation. Okay? But if you run through the computation the efficient way, you go away from topology. Okay? So that's one point. Another point, so this invariant does extend to tangles, okay? But the extension to tangles is hugely inefficient. Basically, if you try to make the same matrix for a tangle, it turns out that you get a matrix with number of rows not equal to the number of columns. And you know, if you want to be able to compute the determinant of a matrix which is assembled by taking 2 such matrices and putting them somehow one next to each other, then you need to know essentially or roughly all the minors of each of the matrices. And the number of minors is exponential in the number of relevant minors turns out to be exponential in the number of components of the tangle. Okay? So, you know, at least as much as divide and conquer is concerned, you defeat yourself, right? Because you took something easy and you replaced it by something for which the gluing work is exponential. Okay? Now there are other extensions of the Alexander polynomials to tangles. So things that come from quantum group theory, quantum GL11, whatever. But these things are also exponentials. You'll get a vector space for each component, and then you'll take the tensor product of these vector spaces, or rather for each leg. But okay, you take a tensor product, you get an invariant valued in the tensor product of a number of things, and that's an exponential size space. Okay? So the invariant that I'm going to tell you about has the lovely property that, first of all, well, it's polynomial throughout. Okay? It extends to tangles, it has good composition properties, and it's polynomial throughout. Okay? Furthermore, the intermediate steps in its computation have topological meaning. Though the topological meaning I will basically hide, because the topological meaning has to do with the four-dimensional stuff I was talking about in the beginning, and by decision I will sort of hide it. Okay? Okay. So what's the idea? So let me first give you the general idea, and the general idea fails. Okay? Okay, and then I'll fix it to something that works. So given a group G, I'll tell you how to try to construct a knot invariant. So given a group G and two Young-Baxter pairs. So a Young-Baxter pair is a pair of elements GO, GU. And I need two such pairs, so R plus and R minus. So I'll have four elements in the group, GO plus minus, GU plus minus. Okay? Then I will map these elements to crossings and multiply along the strands. So meaning, for each crossing, well, each crossing has an over strand and an under strand. So I will put GO on the over strand and GU on the under strand. And if it's a positive crossing, I will put it with superscript plus, and if it's a negative crossing, I will put it with superscript minus. Okay? And then to get the invariant of the tangle, I will just multiply along the components. So in the top component here, well, I first pass as an over strand in a plus crossing. So the first thing I see is a GO plus. Then I'm under a plus crossing, so I'll see a GU plus. Then I'm over, so I see a GO plus. Then I go down here, and these are negative crossings, and I go under, so I see a GU minus, and so on. So for each component of the tangle, I get a product of elements in the group. So I get, well, one big product for the longer component and one shorter product for the shorter component, and that's my invariant. Okay? Well, it will be an invariant if it satisfies the Reidemeister moves. So you check if it satisfies the Reidemeister moves. So you basically, you compute the invariant of this tangle and compare it with the invariant of, that tangle. And this gives you a constraint on those four elements. Basically, it tells you that GO plus is the inverse of GO minus, and GU plus is the inverse of GU minus. Then you see what Reidemeister 3 gives you, and Reidemeister 3 will imply that GO plus and GU plus commute. So basically, all of these elements commute. So since they all commute, you can just sort them. And really, you're counting how many there are of which. So the invariant is just a counting invariant. And if you know what the linking matrix of a knot is, it's actually slightly weaker than the linking matrix. Anyway, it's not interesting. Okay? So the trick is to generalize a group to a meta group. And I have to tell you what a group is, but first of all, I have to tell you sort of a slightly different perspective for how to work with groups. Okay? So given a group, I can imagine a group computer. So something that can work with that group. Okay? Now, a group computer will be able to store data sets containing elements in the group. So a data set will be an element of the group raised to some finite set, sort of the names of the registers in the computer. And you know, this particular data set in my computer has 4 registers in it. A register X storing X1, a register U storing G2, sorry, I said X, I meant X storing G1, U storing G2, and so on. The set of all such data sets with these registers is G raised to this set. Okay? Likewise, here is another collection of data sets. And a group computer will also has operations. So you could tell the computer to apply the operation, multiply the content of register X with the content of register Y, storing the result at register Z. The result will be, well, register X and Y, by my convention, get eliminated. So no registers X and Y anymore, but their content got multiplied and got stored in register Z. Now, this operation, MXYZ, satisfies properties. Okay? So the loveliest of these properties is the one that follows from associativity. Okay? Namely, if you multiply X and Y, store the result in U, then you multiply U and Z, store the result in V, this is the same as multiplying Y and Z, storing in V in U, then multiplying X in U, storing in V. Okay? Now, a group computer, a good group computer will have some further operation. So maybe it will have an operation for inverting the element in register X. It will have an operation for inserting the unit in register X. So this is on the assumption that register X was not in the data set previously. So take a data set that doesn't have a register called X. The operation E sub X will create another register and store the identity in it. Well, register deletion, element cloning, renaming registers, and then all of these are not terribly interesting, but the next interesting operation is the binary operation. So the binary operation takes 2 data sets with disjoint sets of labels and merges them. Basically takes their union. Okay? Now, there are lots and lots of axioms, but they're all obvious. But let me state one axiom which is somehow different than this one. So here's the one different axiom. So if you have a data set with 2 registers, so if P is a data set and it has 2 registers, X and Y, then this data set is equal to the data set you get by deleting Y. Well, if you delete the data set, if you delete Y from the data set, you'll only be left with X, with the register X. Take the same data set, delete X, you'll only be left with the element Y, and if you merge these 2, you get the data set you started from. Okay? Now, the difference between this axiom and that axiom is that this axiom is somehow linear. Okay? So the data set appears only once on both sides of this equality. So basically, you take the data set P, you apply to it 2 operations, and that's equal to P, to which you applied 2 operations once again. So it's somehow linear. P appears only once on either side. Whereas this operation, this axiom, is quadratic. Well, it's linear on the left, but it's quadratic on the right. P appears here twice. So in fact, if I really wanted to write this, I first need an operation of cloning an entire data set. Okay? Good. So what's a metagroup? A metagroup is the same, yes?
Small remark. It's interesting that in many explanations of computer complexity, the cloning is forgotten.
Yeah. And you know, it's also sort of reminiscent in quantum mechanics. So you know, metagroups in some sense are the right quantum groups, except the name quantum group was taken and you know, no way to fight with it, so okay. Anyway, so what's a metagroup? So metagroup is a similar computer, so it has the same collection of data sets and the same operations, except I don't know what the internal structure, and I don't care what the internal structure is. So long as the same axioms are satisfied, but not all axioms. You see, because you see that this last axiom essentially implies that the data set corresponding to x and y is a Cartesian product of the data set of x and y. So delete this axiom, or more precisely, delete the nonlinear axioms. So a metagroup is same as before, but assuming only the linear axioms. So more precisely, for every finite set gamma, the set of names of registers, you get a set G sub gamma, which is the set of data sets, sort of with these registers, okay? And then you have operations mxy da 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 da, and also a union operation, such that all the same linear properties are satisfied. Examples. So obviously example number, oh, I got it wrong. Example number 0 is the non-meta example. So take G sub gamma to take it to be G raised to the power gamma. Not interesting, okay? But there are more examples. So example number 1, take G sub gamma to be the set of gamma by gamma matrices, say over Z, okay? With the operations sort of simultaneous row and column operations, okay? So, you know, if you want to, so you know, an element of G sub x, y, z will be a 3 by 3 matrix with rows and columns labeled x, y, z, and with entries in the integers. And if I wanted to add x to y, I will add the corresponding rows and at the same time add the corresponding columns, so that I'll get a 2 by 2 matrix. Oops, sorry, I mean add x to y and call the output u. So I'll get a 2 by 2 matrix with this labeling. And the entry over here will be the sum of these 4 entries. And, you know, the rest you can determine yourself. Okay? And likewise, all the other operations are defined by do the obvious thing, but at the same time for rows and columns. So this is an honest metagroup. And here's the proof. So take P to be the data set with 2 registers, x and y. So the columns are labeled at the same way, so I'm not bothering to label them. And so deleting the register y will delete the row y and the column y. So you'll be left with only with a 1 by 1 matrix whose single row and column is labeled x. So you'll get this. Deleting the register y, the register x, you'll get this. Oops, I forgot to tell you what this joint union is. So the union of 2 data sets is to take the block diagonal sum of the matrices. Okay? So take the block diagonal sum of these 2 and you get this, and this is different from P. So this is an honest metagroup. Okay? Now, I have plenty of further examples, some further examples. Maybe, I don't know if I should show them now, maybe I should go through my talk, sort of to get to the somehow content part of the talk. But later I will tell you that there are examples that come from group theory, honest group theory, sort of the group of all groups, the metagroup of all groups somehow, and from chord diagram theory, and from, well, various other places. Anyway, one further claim. Suppose you have a metagroup G and a pair of Young-Baxter elements in it. So what's a pair of Young-Baxter elements? it's two elements r plus minus, both of them living in sort of the meta-analog of a pair of elements. Okay, so in G sub 2. Okay, so I guess 2 represents the two element set. So the thing that has two registers in it.
Look at example 1.
Okay, yeah.
G2 is G2.
Yeah, G2 is G2. Okay, so basically, if you have a pair of Young-Baxter elements like that, I can try to imitate the construction of before. So what will it look like? Let me go back to, oops, here it is. No, you know what? Let me go even further back to the nicer picture. Okay, so basically, suppose you give me a knot or maybe a tangle, it doesn't matter. Okay, here's how I will construct an invariant. I will label, I will go through the knot and put two labels in each on each crossing. So sort of one label for the first time I go through it, and then another label for the second time I go through it. So I'll get 1 on the understrand here, 2 on the overstrand here, 3 on the understrand, 4 on the overstrand, and so on. Okay? Now I will take, so this is an 8 crossing knot, so I will take 8 copies of the Young-Baxter element. So 4 copies of R plus and 4 copies of R minus. And I will rename the registers in each of these to the corresponding names. So for the first copy of R minus, I will rename the registers 12 and 1. For the second copy of R minus, I will relabel the registers 2 and 7, and so on. I do have renaming operations. Then I will merge all 8 data sets. So now I have a big data set with 16 supposed group elements in it, except it's not group elements, okay? And then I will just multiply them in order. So I will multiply 1 with 2, store the result in 1. Then multiply 1 with 3, store the result again in 1. Multiply 1 with 4, store the result again in 1. Multiply 1 with 5, just iteratively multiply. At the end, I will get a product, or well, I will get a data set with only one element, and that one element is called 1. That data set will be my proposed invariant. If I do it for a tangle, I will get an output in a data set that has 2 registers, one for sort of the first entry of one component and one for the first entry of the second component, and that sort of data set will be my invariant of the tangle. Okay? Now this has obvious composition properties. So if you want to put 2 tangles side by side, it's sort of clear. I mean, maybe I will not go through it, but it's clear how to multiply. Okay? Basically, if you want to concatenate 2 strands, you multiply. Sorry, you have 2 tangles. You first of all take their disjoint union. You merge the data sets. Then you want to concatenate strands. So if you concatenate strands, you just do it by multiplying the elements written on them. Okay, or the meta elements written on them. Okay, it's not really elements. Okay. And then, you know, if you were lucky and the 2 Young-Baxter elements that you chose satisfied Reidemeister 2 and Reidemeister 3, meaning would give you the same product when you compute the tangle invariant for Reidemeister 2, the 2 sides, right? Also the same product when you compute the tangle invariant for the 2 sides of R3, well then you'll get a knot invariant or a tangle invariant. So is it clear? So this is my strategy.
I didn't see how you used the Young-Baxter element in what you have described.
Well, so for each crossing, I took a copy of the Young-Baxter element. So that's a data set on 2 registers. Then I took the disjoint union of all of these copies, so I got a data set with 16 registers, and then I multiplied these 16 registers in sequence. But in order to start the process, I had to take a Young-Baxter element for each strand, for each pair. Okay? I mean, otherwise, I have no way to start, right? If I just have a group computer, I still have to feed it with something. Okay, is this, did I answer? Any other questions? Okay. So again, I'm going slow because I have time, but you know, if I'm also going boring, maybe you should say so. Where am I? Okay. So okay, the point is, I still don't have good examples. So you know, it's like in ordinary group theory. You know, there is that much examples of groups you can write by hand. Okay, you know, maybe the symmetry group. Okay. But then you want to write more complicated groups, you must sort of have techniques of building new groups from old. Okay? So the same here. Okay, so let me tell you about, well, the process that will actually lead to the meta group that I will study that will give me the Alexander polynomial. Okay? So it's sort of like Bicrossed products of ordinary groups. So let me first remind you what is the Bicrossed product of two ordinary groups. So if you have two ordinary groups, H and T, and both are subgroups. So suppose a group G is the product of two of its subgroups, H and T, and these two subgroups are disjoint. Then it's a lovely exercise that G is also equal to T times H. Okay? But by the way, this is not necessarily a semi-direct product. There are other examples. Okay? And then it turns out that the group G is determined by H and T in a single further map called the swap map. And the swap map is the map that maps a pair TH in T times H to the pair H prime T prime that gives the same product when you multiply. Okay, so basically the pair H prime T prime is defined by TH is equal to H prime T prime. Okay. So basically, all you need to know is if you have a pair H and T, you need to know how to rewrite their product using in the other order. Okay. Now this swap operation satisfies two primary axioms. So the main axioms are two. Then there are silly axioms about the identity and inverses. I don't know. I don't want to write those. Okay. So you know the two primary axioms that the swap map has to satisfy are these two axioms written here. And let me explain. So first of all, my convention is that tails are blue and heads are red. Okay. And then the first axiom says that if you have two tails and multiply them, and then you swap them across a head, you get the same as swapping the second tail, then swapping the first tail, then multiplying. Okay? So that's or written in a sort of formula, tail multiply, so meaning multiplication in the group T, followed by swap, is equal to swap followed by another swap followed by tail multiply. Okay? Likewise, there is an axiom with same thing but with tails and heads playing the opposite roles. Okay? And the moment you have these two axioms, so the moment you have two subgroups, H and T, a swap map which satisfies this axiom and that axiom, which I didn't even write here explicitly, you can reconstruct the original group. And the way you do it is, well, in the original group, elements are represented by HT pairs. Okay, so I just need to tell you how to multiply two HT pairs. You multiply two HT pairs by putting them side by side, swapping the sort of middle TH, and then multiplying the two H's and then the two T's. So I mean, it's written here in sort of element level language. So H1T1 times H2T2 is, well, first of all, you swap the middle two using the swap map. Then you multiply on the left, and then you multiply on the right, and then the result is a product of a head and a tail. Okay? And it's written here in sort of operation or functional language. So the group multiply of 1 and 2 and 1 and 3, of the element 1 and the element 2, putting the output in 3. So an element 1 is really a pair of one head and one tail, and an element 2 is a pair of one head and one tail. So anyway, their group multiply is to swap the tail of 1 with the head of 2, then do tail multiply, then do head multiply. Okay? Now, the point is that all of this makes sense in this sort of meta language. So a Meta-Bicrossed-Product, so a Meta-Bicrossed-Product is sort of, it's sort of a slightly wrong language. Really, it's the meta information that goes into the construction of a bicrossed product. So a Meta-Bicrossed-Product should have sort of 2 meta groups in it and an additional swap map. So for every collection of labels, eta and tau, so eta is a collection of things that label heads. Tau is a collection of names that label heads. So beta, eta, tau will be a set of data sets that store eta heads and tau tails. Okay, so a Meta-Bicrossed-Product information is a collection beta, eta, tau with operations tail multiply. You know how to multiply 2 tails and out. So basically, it will take 2 tails and produce a new tail, and remove them, produce a new one. Head multiply and a swap operation, and then all the lesser operations as well. Such that tail multiply is associative, meaning it satisfies the same associativity axioms that I wrote before. Head multiply is associative independently, okay? And also axioms 1 and 2 of the previous slide, so these 2 axioms, this one and that one, hold, okay? Now, if you have this information, so if you have the information for a Meta-Bicrossed product, you can use it to construct a meta group. Namely, the way you will define the meta group is you will define G sub gamma to be, so now, you know, if I want gamma registers storing elements of G, I need gamma tails and gamma heads. So G sub gamma will be beta of gamma and gamma, and then I will define the group multiply, so the multiplication for the group, the sort of product group, using the formula written here. So using this composition of the given formulas. And you can verify that the moments swap Tm and Hm satisfy the good axioms, the resulting Gm will be associative, will satisfy the axioms for a meta group. Okay? Examples. So maybe, well, okay, example number 0 is the non-meta example. So take beta eta tau to be h to the eta cross t to the tau. Well, example number 1 will be take tau by eta example matrices over Z and use row operations for the tails, column operations for the heads. The swap will be the trivial swap. So this is sort of like a direct product, but it's still not a product of groups. I mean, this is a genuinely meta example. Okay? Okay. Again, I have further examples. So again, there is somehow a meta group of groups, and then there are several other examples. Oh, one other example is in fact the example I started from. So knotted balloons and hoops. Okay, so if you take knotted balloons and hoops like I started from, and use, well, Tm for Tm, Hm for Hm, Sw for Sw, that's an example. Okay, and it's a genuinely meta example because all these operations became unary. Okay. now the primary example. So now the example that actually produces the Alexander polynomial. So let beta of eta and tau be more or less the set of eta by tau matrices. So the same as the previous example, except, so again, the rows are labeled by tails, the columns are labeled by heads, except there is an additional entry omega. So it's sort of, there is an additional, sort of like a central extension, yet another element, okay? And those entries are not integers, but rather all of them are allowed to be rational functions in a variable, a single extra variable x. I guess I'm giving you the simplified version, where at the end you get a single variable polynomial. There is also a version that will give the multivariable the multivariable Alexander polynomial, and then instead of rational functions in a single variable x, you will get rational functions in several variables t sub I, capital T sub I, where capital T sub i's are in a, where these variables are in a bijection with the tail labels. Okay, so there is another, there is a slightly more complicated variant as well.
And what about the coefficients in your functions?
Oh,
It's a rational function in a variable, but
oh yeah, the coefficients are integers, always. Yeah, always integers. Well, you could make them rational. Well, I mean, but they're integers. I think they always stay. No, I know they always stay integers. Sorry. Okay. Now I need to tell you what the operations are. So the first interesting operation is the union of two data sets. So if I have like a disjoint set of registers, head registers, so two sets of head registers, eta 1 and eta 2, and they're disjoint. Likewise, two sets of tail registers, tau 1 and tau 2, and they're disjoint. The way I merge these two data sets is by taking the block diagonal sum of the matrices and multiplying the corresponding omegas. Again, I'm not telling you where it came from. It came from this complicated process that I described in the beginning. Okay. Then the tail multiply, well, the tail multiply is sort of the silly tail multiply that come from tau by eta matrices. So it's not terribly interesting. So the tail multiply of alpha and, okay, so here's how it works. So suppose I wanted to multiply, to do tail multiply to the data set in which I have a tail x and a tail y to produce tail z. So I write the matrix as like the row corresponding to the tail x, the row corresponding to the tail y, and the rest, which I call gamma. Gamma I don't touch, omega I don't touch, and alpha and beta I just add. So it's basically row operation. Okay?
When so you have those things belonging to the set that indexes rows and columns, you were saying that H, J are in eta, T, J are in tau, but they're not allowed to repeat.
No, they're not repeating, right.
So it's subset of...
No, it's not subset. I mean, this is the entire set tau, and this is the entire set eta.
Okay.
Okay? It's,
they just are listed in...
yeah, they're listed in some, it doesn't matter which order, right? Okay? Okay, next, I have to tell you what the head multiply and the swap are. And that's where things get slightly complicated. So first of all, given a column in a matrix, I define the norm of the column to be just the sum of its entries. Okay? And then, if I wanted to multiply, to do head multiply of x and y storing the result in z, so I'll get the column corresponding to x, it's alpha, a column corresponding to y, it's beta, and the rest gamma. Well, the operation doesn't touch the rest and doesn't touch omega. But what you do to the columns alpha and beta is you sum the columns, and in further you add a further copy of the column beta multiplied by the norm of alpha. So I mean, you cannot argue. I'm defining. Okay. Finally, there is the swap operation. The swap operation is where it's the most complicated. So I want to swap the tail x with the head y. So I write the matrix as a sort of a block form, okay? So alpha will be the scalar in this row, in this column. Beta will be a row of size kind of eta minus 1, the norm of eta minus, the number of entries in eta minus 1. Gamma will be a column vector, and delta will be a 1 less by 1 less matrix. And then the swap operation will do the following. First of all, you'll take alpha. You'll form epsilon to be 1 plus alpha. You'll take omega and multiply it by epsilon. And for the new matrix, you'll put this sort of funny things in the as its entries. So the scalar will be alpha times 1 plus the norm of gamma divided by epsilon. A similar thing for this row. The column gamma will simply be divided by epsilon, and the block delta will be replaced by delta minus gamma times beta divided by epsilon. Now, gamma is a column, beta is a row, so gamma times beta is, again, a n minus 1 by m minus 1 matrix. So it all makes sense, at least. Finally, I claim that there is a Young-Baxter pair. Here it is. I'm just, again, writing. I'm just telling you what it is. You cannot argue. But then comes the theorem. The theorem is that, okay, first of all, this is indeed a Meta-Bicrossed-Product. And second, these two elements are a Young-Baxter pair. They satisfy Reidemeister 2 and Reidemeister 3. The resulting invariant is all that I ever all that I wanted. So it restricted to knots. If you look at the omega part, so this part will be the Alexander polynomial. Actually, it turns out that sort of the big block will be a 1 by 1 block if you're talking about knots, and it contains non-interesting information. So within the computation, it contains interesting information, but the end result is not interesting. But omega contains the Alexander polynomial. Furthermore, it contains the multivariable Alexander polynomial and several other related things, once you think about it in the appropriate way. And furthermore, it has good composition properties. Well, exactly the good composition properties I told you about before. And furthermore, everything all along is polynomial. The amount of information that I have to store is just n by n matrix at any given amount of, at any finite amount of time, at any specific amount of time. So maybe should I tell you why I'm happy? I think I already told you more or less. Maybe I'll add that sort of one reason why I'm happy is that everything fits on one sheet of paper, including the computer implementation. So let's go to the computer implementation. I mean, I really mean, this really is useful for computation. So here's the, well, this is the non-interesting part of the program. This is the part of the program about pretty formatting of the output. Ignore it. Here's the interesting part of the program. So it's a bit hard to see.
What is your code?
What?
Kind of code?
Mathematica. Okay? But this is the whole program. So maybe I will not go through the syntax, but if you read it carefully, you'll find that the exact same formulas that I wrote on the handout appear here. So here is the formula for the swap operation. Okay? So first of all, alpha, beta, gamma, and delta are defined to be various coefficients of the input. And then you just form this. Okay? So that's the full program. And now, once I have a program, I can actually use it to test the axioms. So, you know, if I wanted to test that this Meta-Bicrossed-Product axiom is satisfied, well, I simply enter a generic element, okay, and then I apply to it the tail multiply and then the swap, or alternatively the swap and then the tail multiply, and I, how do I do that? I mean, I hit enter. Oh, I first of all should have entered the program. Then I hit enter here, and the output is true. So I mean, believe me, that if you run the same program with wrong input, it outputs false. So I mean, I didn't fake, I didn't lie. Okay. Likewise, if I want to check that something is that the Reidemeister 3 is satisfied, and in fact this is sort of a case of divide and conquer. In order to prove that you get a not invariant, it's enough to concentrate on a little tangle because everything is multiplicative. Okay, so I compare the invariant of this tangle with the invariant of this tangle. This amounts to labeling everything, and then the top tangle becomes R minus times R minus times R plus with certain group multiplications, and then, well, same for the second one. Again, you hit enter. This time I didn't compare, I just printed the output, but you can visually compare, and they're the same. Okay? Finally, here's how it works in sort of more real-life situation. So take the 817 knot, the same knot that I started from. It's an 8-crossing knot. There should be 16 registers, 16 tail registers and 16 head registers. But if you look at the Young-Baxter elements, most of the rows and columns are 0. Well, sorry, I mean, there's only one non-zero entry. So my program automatically suppresses, this is the pretty printing part of the program, it automatically suppresses zero rows and columns. So the invariant of, or rather the disjoint union of 8 crossings, the invariant of that is a 16 by 16 matrix whose labels are H1 through H16 and whose row labels are T1 through T16, but most of the labels are dropped because the corresponding rows and columns are empty. So you get an 8 by 8 matrix, and here it is. Okay? Then you have to hit enter. Then you tell the computer, apply the group multiplication operation of register 1 with register K, put the output in register 1, and do it for registers 2 through 10. Well, I should be doing it to 16, but I want to stop in the middle so that we see what happens. We hit enter, and, well, omega got changed, and we got a non-trivial messy matrix in the middle, but, well, something, okay? Then I tell the computer, do the same, but now for K going from 11 to 16, hit enter, and you get, well, the Alexander polynomial. So here's Alexander looking at it happily because he knew the result from before. Okay? I gave you the content part of my talk, but now I can do sort of lots and lots of discussions. So, okay, here's my to-do list. So first of all, this thing came, I told you where it came from. It came from a complicated place. But it must also come from a simpler place. So I'd be happy if Jake will tell me where that place is. Or maybe somebody else. Okay? Now, if you look at the formulas, they have denominators. Now, it's not so easy to show, but possible to show that the denominator, this is not the best example, but it turns out that the denominators are always omega. But it's not trivial. It's not obvious that, always divide omega. So if you multiply the matrix by omega, it becomes a matrix of polynomials. But it's not an obvious property. It's not obvious that this property is preserved by the operations. So my question is, I suppose, how to make it obvious. Now, okay, so at the end, this formalism computes a certain determinant. I have no idea why. Okay, so in fact, the proof that I have that this is the Alexander polynomial, well, I have two proofs that this really is the Alexander polynomial. One proof is to go through this chain of complicated reasoning of where did it came from, And using it, eventually you can get a proof of the fact that it's the Alexander polynomial. But it's, again, a roundabout proof. The real proof, the real reason why I believe it's true, I mean, I don't believe myself when I do complicated things. So the real reason why I believe it's true is because I computed it for all knots with up to 11 crossings, and it works. So, I mean, it's indisputably true. But it's still missing an honest, simple-minded proof. How does this formalism compute a determinant of some specific matrix? Okay, what about links? So you see, really this is an invariant of tangles. Now, so-called 1-1 tangles, so tangles with just one end are the same as a knot, are the same as knots. Because if you have a tangle with one end, with just one input end and one output end, you can connect the two and you get a knot. And furthermore, if you have a knot, you can cut it open, you get a 1-1 tangle. And you can show that it doesn't matter where you cut open. You'll always get the same 1-1 tangle, modulo Reidemeister moves. Okay? This is not true for links. So every link is the closure of a tangle. So if you have an n tangle, so a tangle with n input and n outputs, you can connect the inputs to the outputs and you'll get a link. But the link doesn't determine this the tangle it started from. So basically, the problem is that, suppose you have a two-component tangle. Let me draw the two components like this. Okay, but they can be tangled with each other, and there could be more component as well, okay? But in this two-component tangle, well, you can make it a one-component tangle by closing it at the top or by closing it at the bottom. Okay? Now, these two one-component tangles that you get, it's not really one distinguished component because there could be more. Okay? But in these two one distinguished components that you get, the bottom closure or the top closure, both of these have the same overall closure. Okay? So here are two distinct tangles, the top closure and the bottom closure, whose closure is the same link. But you see, this is stated using the this is really rephrased using the meta-group operations. So, if I wanted to get an invariant of tangles, of links rather than an invariant of tangles, I would have to look at some sort of beta space modulo the image of multiplying x and y to get z is set equal to multiplying y and x to get z. So basically, I will have to somehow look at the meta-coinvariants of my beta space. Okay. Again, I can make it precise, but this is the schematics. So the to-do part of this is to really understand the meta-coinvariants of this specific meta-group that I've constructed. So I don't understand it. I do know it is non-trivial because I do know and I know how it contains the multivariable Alexander polynomial for links. But I don't know if and what else it may contain. Okay. You know what? Maybe I'll skip the reality condition, but I'll tell you what is algebraic knot theory. So, algebraic knot theory is a bit like algebraic topology. So, sort of naive homology theory is you get invariants of spaces, namely the homology. Better homology theory is where you also notice that when you have a map between spaces, you get maps between the corresponding homologies, and therefore you can use it to solve topological problems. So if you want to show that there is no retract from D2 to S1, you do some, S1, D2, S1, something, compute homologies, and the the sort of algebraic diagram does not exist, and therefore the topological diagram does not exist. Now, the moment you have operation, the moment you have an invariant of knots that is well behaved with respect to certain operations, then you can ask, then you can use it to study properties of knots. So if you have a property of knots that is definable using these operations, then applying the invariant will give you information about this property. So that's the general philosophy, but here is a specific example. So there is something called ribbon knots. So it's a subset of the collection of all knots. Okay? I'm not sure well, you know what, maybe I will define it. So a ribbon knot is a knot that has that bounds a disk which is allowed to be singular. Well, every knot bounds a disk if the disk is allowed to be singular. But in a ribbon knot, you have a limited type of singularities. The only singularities that you're allowed to get are so-called ribbon singularities. So the disk sort of looks, the singularities look like two ribbons that intersect each other. So basically, the double points will only occur here, and the inverse image of the set of double points in the parameter disk will be two intervals, one going from the boundary to the boundary, and another one going from an interior point to an interior point. Okay? This is as opposed to so-called clasp singularities, where you have a picture like this. So this is one part of the disk, this is another part of the disk, and they intersect in a line like this, which is not of this form. Okay? So, well, I just gave you a topological definition of ribbon knots, but it turns out that there is also an algebraic definition of ribbon knots in terms of tangles. So, a knot is a ribbon knot if and only if you can find a tangle T which has the connectivity. So T is written here in green, and the dotted line indicate the connectivity. So this end of the tangle is connected to that end of a tangle by a strand, but of course this dotted line can be a link tangled with the other dotted lines. So take such a tangle, and here are two ways of forming a closure. One way is to close it by adding on the outside, like sort of caps, 4 caps in this case. The other way is to take that tangle, turn it one notch counterclockwise, and then do the same closure. If you use this closure, you'll get an n-component link. Well, 4 component in this case. If you use this closure, you get a knot. So a knot is a ribbon knot if and only if there exists a tangle T whose first closure is a trivial link, and then the second closure will be our knot. Okay? And if you want an example, here is an example. So an exercise for you is to check that if you close this way, closing this to here and this to here, you get a trivial link. You can sort of see things slide out. Whereas if you close it bottom to bottom and top to top, you get a non-trivial knot, and in fact that knot is a ribbon knot. Okay? So basically I have a definition of ribbon knots in terms of tangles and tangles operations, and this means that my invariant, or this Alexander invariant, should be able to say something about ribbon knots. So, well, there are actually known things about ribbon knots and the Alexander polynomial. So the first exercise will be to reproduce the known things. The second exercise would actually be to generalize this picture to other knot invariants and then say more, okay? But again, this is a long-term to-do list. Finally, maybe the last thing is to, the last item on my to-do list is to categorify this. You know, if you're looking for a candidate, and a good Alexander candidate to be categorified, I think this is sort of the best. So, but, you know, I don't know what else to say. I have more, but I'll skip and move on to the propaganda, which also fits on that one page. And if people want me to give further examples of meta groups, then where are they? Then I could. And alternatively, people should tell me that I'm an idiot and meta groups should be actually called something else. You know. Or well, okay. So I don't know if I should do more or not, but I'm happy either way.
Just thank you first. I will that to see if people ask questions, and then maybe we go on. So, do you have any question?
Yes.
Vas-y.
You never use the inverse of.
Yeah. So really, I'm lying. Sort of, it's a Cachinay meta group, and in fact, this is a meta group. Well, actually, it can be easily corrected to become a meta group. But to get knot invariants, I don't need meta groups. I only need meta-monoids and Meta-Bicrossed-Products of monoids. So you're right. Now, the doubling operation does have a knot theoretic meaning, and the meaning is to take a strand and double it. And indeed, you know, if you kind of if you take a strand and then double it, and then apply the inverse, so reverse the other strand, and then multiply the two strands, what you get, well, this is a finger that you can sort of slide down, so this is the identity. So somehow the operation of doubling a strand, so somehow tangles are inherently a meta group and not a meta, or more precisely a meta Hopf algebra, and not a meta which is more than a meta monoid. But I don't need this for the story that I told. Yeah. Maybe I should also say, sorry. Now this is I'm jumping way too far. Extending the beta calculus, not the beta calculus. So beta calculus is a projection, as I said, of some universal associated graded calculus. So extending that universal associated graded calculus to be a group calculus rather than a monoid calculus is precisely the Kashiwara-Verne problem of Alexeyev and Torosian, in the language of Alexeyev and Torosian.
Can you say it again?
So, okay, I did not tell you that this is I did tell you, okay, that this is all a projection. There is a fancier calculus that has to do with Freely algebras, etc.
Yes.
And this is all just a quotient, a summation of a quotient of that fancier Freely calculus. In the fancier Freely calculus, there exist the same operations: tail multiply, head multiply, and swap. But if you want to extend it so that it will also have a doubling operation, so the doubling of a register, then properly doing it is essentially the Kashiwara-Verne problem. It's a question about Freely algebras, and well, and wheels and loops, and it's the Kashiwa-Verne problem. But again, this is a lengthy story. I mean, I yeah.
Do you understand how to get the Alexander polynomial scheme relation? It seems like that's...
No. Other questions?
Any other question? Okay. I propose that we thank you again.